Welcome to Botronix Labs. In this tutorial, we bring everything together from our fundamental robotics programming course to build and program the Pico Otto Robot Car, an open-source robot based on the original Otto DIY design. We gratefully acknowledge the Otto DIY project and community for making their 3D printable robot platform open and available under an attribution license. This project wouldn't be possible without their amazing contributions. This robot includes multiple components we've worked with throughout the course. 2 continuous rotation servo motors for driving the wheels. An ultrasonic distance sensor for obstacle detection. An active buzzer for alerts. A 7-segment LED display for visual expression. A sliding power switch and 2 battery pack as power source. I have removed the green LED since no room for it in the Otto head after applying 2 batter packs. Watch the Module 5b video for detailed installation tutorial. We've wired each component to GPIO pins on the Pico and powered them with dual regulated battery packs. The ground is shared across all parts to ensure proper circuit operation. Take a moment to carefully wire everything based on the full circuit diagram. Make sure the power switch controls both logic and motor power, and test each component individually if something doesn't behave as expected. Now that we've assembled our Pico Otto Robot Car, let's walk through the full MicroPython code that brings it to life. We start by importing all necessary modules. This gives us access to GPIO control and timing functions. We set up the 2 servo motors on GPIO 14 and GPIO 13 using PWM. The frequency is set to 50 Hz, standard for continuous servo control. Next, we configure the ultrasonic sensor. Trigger sends the sound pulse. Echo receives the reflection. The buzzer is connected to GPIO 4. It turns on when an obstacle is near. We use GPIO 17, 18, and 22 to control selected segments B, C, and G. This gives a simple mouth expression. We define functions for forward, backward, stop, and turning. You can adjust these values to tune the speed and behavior. This function calculates distance using the ultrasonic sensor. We multiply by the speed of sound and divide by 2 to get one-way distance in centimeters. Here's the main logic controlling behavior. This code checks distance continuously, alerts when too close, executes a backup and turn maneuver, displays expressions accordingly. This complete code demonstrates a simple form of robotic perception and response using sensors and actuators. It's a great way to understand how embedded systems bring physical interaction to life. You can download the complete code using the link in the comments section. In this final part of the project, we bring together all the components you've assembled and coded in previous steps to demonstrate the full functionality of the Pico Otto Robot Car. Once the power is switched on, the robot initializes by displaying a mouth shape on the 7-segment LED, indicating it's powered and ready. The robot drives forward slowly. Using the HCSR04 ultrasonic sensor, it continuously measures the distance to obstacles ahead. If an object is detected closer than a set threshold, e.g., 10 centimeters, the robot stops. It emits warning beeps using the active buzzer to simulate an alert system. Then, it performs a reverse and turn maneuver using the 360-degree servo motors, giving the appearance of intelligent avoidance. The 7-segment LED provides visual feedback. When avoiding obstacles, the robot briefly changes the display pattern to resemble a different mouth expression, mimicking emotion. This entire behavior loop continues until power is turned off. It demonstrates basic robotics concepts: sensor integration, feedback control, and multi-component interaction using MicroPython on the Raspberry Pi Pico. And that wraps up our Module 5 project, the fully assembled and programmed Pico Otto Robot Car. In this video, we combined everything we've learned so far. This has been a great hands-on demonstration of real-world embedded systems, and I hope it gave you a deeper understanding of how hardware and code work together. Thanks for following along, and see you in the next module.